Well, thanks for inviting me to talk tonight. As Bob just said, I used to be an astronomer, and as I think you should see on this picture in front of you, let me just do this. This is the telescope I used to use, but it's 50 years since I used telescopes. This is the 98-inch Isaac Newton telescope, which at the time was based at Hurstmonceux near Hastings. It's now based in the Canary Islands, where you can imagine the night sky is much clearer and they get a lot more photographs out the top of it. When I was using it, I actually used to sit in this black area up here, along with the scientific instruments I was using at the time, and I'd be up there for a few hours at a time. And since I retired, my plan was to start doing some astronomy again, but actually I got interested in I suppose the sort of like textbook or paper-based type studies of what goes on in the universe. And I've been looking at galaxies and supernovae and quasars, just looking at the data that's available, amazingly publicly available in billions of bytes of information about all these things. So I'll tell you about that later. The main thing today was to cover the topic of quasars. And I know there's a range of knowledge and interests in the society, so please bear with me. I'll try and do an introduction over 10 minutes just to set the scene for the later discussion about quasars specifically. So just to sort of kick that off, our universe, as you all know, probably consists of a number of types of things, shall we call it, and I'm just going to go through a few of those. So dust, electrons, protons, atoms, molecules, as it builds up into small particles of dust, and that varies in density across our galaxy and the universe. The dust can gather into planets, moons, asteroids, smaller bodies that exist in our universe, and those planets, moons can be hard rocks, and some planets, as you know, with Saturn and Jupiter are mostly gas. And as the gas bodies accumulate in size, they turn into suns and stars that we see all around us. So every star is another sun, and they're primarily, suns are primarily hydrogen and helium atoms. Moving on to a bigger scale, we see that those suns gather together in galaxies, and I'm sure over the years you've seen lots of pictures of galaxies in this group. And then there's the subject of quasars, which we'll be talking about tonight. And as you see on this photo, there are things on this photo that look like gas. There are things on this photo that look like stars, and there are things in this photo that look like distant galaxies. And it's very hard to tell this object as being different from these other objects. And that's why they weren't discovered until the early 1960s. So that is a quasar, and I'll be talking more about those later. But let me just continue this introduction a little bit further. And I think this is a fairly complete list of things our universe contains. You might think of others, but dark matter and dark energy is the subject of a lot of scientific research at the moment. My view on those is, do these things really exist as separate items, or is our knowledge of physics and the way our universe operates certainly can't explain some of the things we see out there, and we do need to have something else that comes in to help get our understanding of the universe to 100%. But at the moment, dark matter and dark energy are potentially helping us explain what goes on out there, but even they aren't helping us fill all the gaps in our knowledge. So that's a list, but let's talk more about quasars. But first, let me just remind you, as I think probably all of you guys know, all astronomers can do really is look at the electromagnetic spectrum, the light that originates from stars and galaxies. And that light is in the form of photons, and the photons vary in wavelength from very short, very high energy gamma rays through our visible light that we see day by day from our own sun, right through to radio waves, which are kilometers long, possibly. And astronomers have telescopes and instruments that look at all of these. And it's that variety of instruments and analysis that helps us understand and differentiate quasars from other objects in the sky. I should also mention we can also nowadays measure gravitational waves that come from objects, but there's very few objects that can emit the gravitational waves that we can detect on Earth at the moment. So that's why I just focused the previous slide on electromagnetic information. And so a spectrum of light from a body consists of, in an ideal world, physicists would show you a diagram like this to say the light from a typical body that is radiating light as heat would be a spectrum of light like this. So the most intense light would be about 5,000 angstroms in wavelength, and we would see less light at shorter wavelengths and longer wavelengths in a profile like this. But that's the ideal spectrum. On the right, we see a typical spectrum from a real star. And you see on here lots of lines. These lines are just identifying elements that cause peaks and troughs in the spectrum of a star. And you see there are many smaller and bigger peaks and troughs. And we are able to identify what causes lines at various wavelengths by our knowledge of physics and tie those lines, I can't even read these myself, to different types of elements, oxygen, nitrogen, heat, hydrogen, etc., etc. So we use this information to help us understand what is happening in various stars. And as that information gathers even for galaxies, we can still see a galaxy spectrum and still identify certain lines, and that helps us understand what's happening in those galaxies. And so understanding the spectrum, understanding the intensity of light at different places in that spectrum helps us understand the something about the object that's emitting the light. But another factor is the redshift of an object. And so at the top, we're just seeing something like the previous slide, and the information displayed in a different way. This is showing you the intensity of light in the visible spectrum from the blue to the red. And it is showing that in that spectrum, there are a number of absorption lines where the information just hasn't reached the Earth from the source. And that information is being absorbed by certain elements. And those elements always create lines at these various points in the chart. And so if an object is what we call redshifted, what we simply mean is that those lines all appear to be shifted to the right by the same amount, as you can see in this diagram. And blue shifted means they're simply shifted the other way towards the blue end of the spectrum. And the redshift or blue shift, we've learned by our understanding of the Doppler effect, which applies to sound waves, but it equally applies to light waves, means an object, usually means an object is moving towards us or away from us. There are other potential sources of redshifts and blue shifts, but the vast majority of things that astronomers look at, the redshifts and blue shifts are generated by movement of that galaxy, or object, I should say, towards us or away from us. And that information was actually the source of a major developing our understanding about 100 years ago by a chap called Edwin Hubble, who produced this diagram in that he measured the distance to galaxies using a number of techniques that are well proven. I won't go into all of those different techniques, but independently, he said, oh, let's have a look at the redshift of those objects. And he was able to draw a graph like this one. And it's an amazing sort of straight line relationship, which occurs at nearer distances to us. It's not so straight at higher distances due to the relativistic effects. But this really helped us understand, some of these differences from the line can be due to measurement errors, either in the measurement of the redshift or in the measurement of the distance, the different techniques used to measure distance. But you can also see here that there is a group of galaxies that seem to have the same distance, but quite different redshifts. And these were identified as a galaxy cluster. And that shows the impact of the cluster dynamics, then that those galaxies are moving, some of them are moving towards us, some of them are moving away from us. We can't detect if they're moving sideways within that cluster, but certainly we can detect if they're moving in a direction towards the Earth or away from the Earth because of the Doppler effect, and that shows up as a chart like this. So when we're measuring redshift, we're fairly confident because of the experience of thousands of galaxies that this line is linear at low redshift levels, bearing in mind that some of the elements of the redshift can be due to the Doppler effect of just local motion by those galaxies. And just as a little introduction, because I've been talking about that, looking at our first slide about quasars, this is another view of the redshift and wavelength relationship. And what we've got here is data for thousands of quasars, each drawn as a line across the page. Whoops, let's go back to that. Each quasar will have a line across here, and that line is drawn at a point related to its redshift. And so you can see as the redshift increases, something that like magnesium 2, which that looks like it must be a bright line in that spectrum, that's seen at a low redshift at about 4,000 angstroms. As we go higher in redshift, that line is moved to the right, it's redshifted along this line here. And we see that for many different elements that on this diagram. So that was a way of showing that the reality that redshift and wavelength are related, and things are redshifted. And as you can see, these lines are not linear at larger scales, and that's due to the relativistic effect. So getting to redshifts of 7 or 8 is very rare because those objects are just so distant and so redshifted that it's very hard to see their visible spectrum. So there's the background. Now let's start talking about quasars. Quasars, as you maybe identified from the earlier slide which showed a quasar, are quasi-stellar objects. So quasi means, to all intents and purposes, they look like a star. They were first discovered in 1963, and there are now hundreds of thousands of quasars identified. So it's not just a one-off type finding. We now know lots about quasars. And they appear not to be a star because their spectrum is very different from a normal star. They have peaks and troughs in different parts of their spectrum, for example. They're often a radio source. They have a large ultraviolet source within their spectrum. They have broad emission lines in the spectra with absorption lines in some cases. And the spectrum typically indicates a high redshift. And another interesting thing about quasars is, like some stars, they vary in brightness, typically over months and sometimes over days. And if the whole object can vary in a period of days and months, that means the object must be very small and typically just a few light months across. When you consider a galaxy like the Milky Way is 100,000 light years across, then we are seeing objects that are called quasars that are much smaller than a galaxy, maybe 1 light year across, not 100,000. So that makes them very odd because they're very bright, they're not stars, and they have this ability to vary in brightness quickly. So if the redshift of a quasar indicates distance, most quasars are very distant. All quasars are very bright, often brighter than the brightest galaxies. And here's a picture of the first one that was discovered. It's an image from the Hubble Space Telescope. And this was discovered by Alan Sandage in the early 60s, as I said earlier. And not only have we identified a quasar in this image, this appears to be a jet originating from that quasar. And if the quasar is at the distance indicated by its redshift, which is about 0.159, I was told, that means that that area of our photo must be 200,000 light years long. And that itself is bigger than our whole galaxy. So this object here appears to have emitted something for a distance of several 100,000 light years from it, that itself is a a couple 100,000 light years long. I just find that amazing. What on earth could this object be at the center of the photo that can be that bright and can emit something like that in a straight line over a long period? So that was one of the things that what made me want to find out more about quasars. And here's some pictures of quasars at different redshifts. And these are the quasars at the center of the photos. And you can see they get a bit fainter and a bit redder with distance. And on the right of this, you can see the spectra or spectrum for each of these objects. And the first thing I thought when I saw these spectra is, how on earth can these be all identified as the spectra of quasars, because they look to me to be totally different. And this is where my expertise fails. You know, I'm reporting information that I've picked up from the internet and reporting the skills of others who are able to identify, as you see these little lines, I hope you can see on your pictures, these identify the various elements, and they consistently show the right separation and peaks at the expected points for various elements. And that has helped identify the redshift and the consistency of information across the spectrum that identifies these items as quasars. Looking at the galaxy M87, this is a real galaxy you can see in the skies. I don't know, I haven't noted its magnitude. Some of you may have looked at this. It is a very compact galaxy, and as you can see here, there is a halo of stars around it. And as you look into the center of that galaxy in more detail with various techniques and tools, astronomers have measured that the velocity dispersion of the stars in the nuclear region rises rapidly towards the center of that galaxy. And it's a strong emitter of X-rays, so it requires a huge energy production at the center of this galaxy. And the central luminosity of that galaxy is higher than normal. So this is actually what's called an active galaxy. And one of the reasons it's called an active galaxy is because, again, this is a different photo from the previous one I showed you. It's a different object. But this one also has this amazing line of who knows what it is, gas and light and whatever emitted from that galaxy. So this is a very active galaxy that has been active for hundreds of thousands of years, emitting something in a very straight line over a very long distance. And looking at the characteristics of the nucleus of M87, we find that it has many characteristics that are similar to the quasars in terms of the ultraviolet light and the X-rays, et cetera, et cetera. So galactic nuclei like this are called active galactic nuclei, and a chap called Seyfert, they're often called Seyfert galaxies because he classified them. They form about 2% of the class of spiral galaxies. So a small percentage, but a significant percent of galaxies appear to shrink to this type of galaxy, and they become very active in terms of the types of light that they emit and even the types of object that they emit. And the major distinction between a quasar and a Seyfert nucleus of the nucleus of the galaxy is simply that we can actually see a physical galactic envelope around the galaxy. We can determine it is really a galaxy, whereas in a quasar, we just can't see an edge to it. It's just like a star. It is just a very bright star-like object. And the argument that for the redshift of a quasar to be of cosmological origin rests mainly on the continuity of properties between Seyfert nuclei and quasars. When I got first interested in quasars a number of years ago, I really believed that they were just objects around our own galaxy. I couldn't believe that they were so bright and so distant. But over the years, mine and most other astronomers' views have changed to say, yes, the redshift of the quasars must be mainly of cosmological origin because of this relationship with the active nuclei of safer galaxies. Another reason for the view that quasars are definitely a long way away is pictures like these, which are showing gravitational lensing to be operational. So at the center of each of these images is believed to be a galaxy. And surrounding that galaxy in different forms is a lensing effect of a distant quasar, and its light is bent around these other galaxies in a way that then we can see in different forms around that galaxy. And we know these objects in this example here, where we see 4 manifestations of the original quasar. We know it is one quasar because we can detect the spectrum of those objects and show that they are essentially identical. And we could also see the spectrum, as I said earlier. Quasars do vary in brightness, and these objects around this galaxy all vary in intensity of light and brightness of light with the same timescales. So that sort of demonstrates that very distant objects gravitationally lensed by the central ones. But then again, we see pictures like this one. Well, it's not a picture, this is just a diagram to show the relationship. Around NGC 3516, we see 5, 6 objects that are all identified as quasars, but all these quasars have different redshifts. And it's very unusual and very unexpected, very unlikely, that so many quasars would be seen in the vicinity and surrounding, in some sort of almost linear way, a particular galaxy. So, excuse me, a number of astronomers believe, rightly or wrongly, that maybe quasars, or some quasars, originate from a galaxy, and in some ways they might have been emitted by that galaxy. However, there are none of those quasar redshifts appear to be blue shifted, as if those quasars have been emitted towards the Earth, and therefore would have a lower redshift than the originating galaxy. But still, it is unusual that there is this pattern around a galaxy, and it's not the only one. There's many more, and here's another picture, which I find more compelling. So this is a galaxy NGC 7603 on the right, and you can see its redshift. And you can see around this galaxy, nearby this galaxy, there are 3 objects. Object 1 is this bright one, 2 and 3 are here, and there appears to be a bridge of light and matter between the galaxy NGC 7603 and this object 1. And it's just amazing that these other 2 objects are in line with that bridge. Is that just an amazing coincidence, or is it an example that quasars do not have all of their redshift associated with distance, but maybe all these objects are at the same redshift as the galaxy, 0.029, and therefore there's a significant additional redshift in these other elements that is not cosmological, is not related to their distance away from us. So quasars have a number of conundrums, and we'll go into that in more detail later. But just to summarize everything in the Wikipedia definition of a quasar, they're extremely luminous, probably active galactic nuclei, and probably with a supermassive black hole there, which ranges in size up to billions of times the mass of our sun. And that supermassive black hole would itself be of mass larger than our own galaxy in many cases. It's believed the quasar is surrounded by a gaseous accretion disk as matter collects to it because it is so massive. And as the gas falls towards the black hole, energy is released in the form of the radiation, which can be observed across the electromagnetic spectrum. As I said earlier, this is the only way astronomers can identify these X-rays and ultraviolet rays, and gamma rays are often sourced from quasars. And that power is enormous. And thinking about the size of the quasars and the luminosity that we measure, some of them are thousands of times greater than a galaxy such as the Milky Way. It's an amazing amount of power. And so they're linked, as I said earlier, towards the class of active galactic nuclei. And in Wikipedia, it says the redshifts of quasars are of cosmological origin. I personally am not convinced all the redshift of all quasars is, but equally, I believe some of it is associated with that. We'll tell you more about that in a moment. So what are the conundrums of quasars? If the redshift of quasars indicates their distance, quasars are brighter at farther distances. So is there some evolution of quasars since the Big Bang? I'm not convinced myself, although the vast majority of astronomers are convinced there was a Big Bang. And maybe this is evidence that there was a Big Bang, and quasars, there was a lot of them at the start of the universe and the early life of the universe, and there's not so many nowadays. Quasars are very, very luminous. I can't even describe how luminous they are compared to galaxies. What could be the source of their power in a distance that's only a light year across? It's just amazing how it operates. And it's not just that quasars are brighter at farther distances, they're found more frequently at large distances. So has that mechanism for creating quasars changed since the time of the Big Bang? However, some quasars are connected to, might be connected to galaxies that have a much smaller redshift. So is that true or not? We need to sort of try and investigate this further. So the key question I sort of started off my research into was to say, does the redshift of a quasar indicate its distance? Or might part of the redshift be independent of distance? And so I knew there was data for hundreds of thousands of quasars available. What might it tell us? And in order to study the hundreds of thousands of quasars, the next question I asked myself is, at any redshift, what might be the count of quasars versus brightness? What might that tell us about quasars on their origin and their evolution? And I thought, well, what sort of things could I expect? Let me sort of think in theory before I study it. And this will also help you guys if I just walk you through this before you see the later slides. I thought, let's consider boulders and stones on a hillside. There are relatively few large boulders, and then as the size reduces, there's more and more of the smaller sizes until we get down to the small stones and grains of sand. And so if we look at a chart like this, we would expect this is the count area up here, count column, and then across the bottom, I'm thinking we show larger boulders, we expect relatively few, and as the boulders get smaller, we'd expect more and more. And I thought, well, we should probably see a similar profile for quasars if they follow this sort of pattern, that we'd see fewer brighter ones, maybe a magnitude 15, we might see them. And then as we go to fainter and fainter magnitudes for the quasars, then we would see more and more of them. And actually, that profile is exactly what we see for galaxies. We see relatively few of the brightest galaxies. And as we look at fainter galaxies at any particular distance, that's not in the sky in general, this is all at the same distance, we would expect to see more and more, and we do measure more and more galaxies, count more and more galaxies at fainter levels, assuming they're all at the same distance. So are quasars like that? Well, we'll see in a moment. But another thought I had was, might the counts of quasars be like the counts of a crop of apples, where we're actually measuring the size of the apples? So we might, in a crop of apples, have a few very small ones, and then the counts in the crop would increase to the normal size of a typical apple. And then as the apples got bigger in size, the counts would go down. And we see what's called a normal distribution curve, sometimes called a Gaussian curve, like this. And I thought, well, maybe quasars might be in the sky like this as well, that there's a few bright ones, and there might be a certain size that they're most often seen as, and then there might be a reduction in the counts as they get even fainter, assuming they're all at the same distance. So that's what I was looking for. And my research approach was to count the number of quasars in each redshift increment and look at the profiles of the quasars in that redshift increment, and then count how many quasars we find in each luminosity increment of 0.1 magnitudes. And again, just to help you understand the later slides, what would an exponential quasar luminosity distribution look like? So like galaxies, we would expect to see few bright galaxies and more counts at fainter galaxies at a particular redshift. However, telescopes have limitations, and we would expect at some point the counts to start dropping off because telescopes just can't see the fainter and fainter objects. And if we look at further distances away at higher redshifts, we'd expect the counts to start later. Because the redshift increment and the volume of space we're counting in gets larger at larger distances. If you think of a shell around a beach ball and the same size shell, but the size of that shell gets larger and larger the further out we go, then we would see a larger volume of space, so we should see an increased count. But of course, that count would then reduce at a similar point because of the telescope limitations. So there's a theory. And yes, that occurs up to a redshift of 1 for the redshift counts. And alternatively, if we were seeing a normal distribution of quasars, we'd see lower redshift a count like this, which increases to be the point where there's the peak of the counts. And for a more distant shell around our universe at a higher redshift, we would see a bigger count, and we'd see it shifted to the right because they're further away and therefore fainter. So there's the theory. What did I find in practice? Well, I looked at the Sloan Digital Sky Survey. I was able to download to my computer, my little PC, 750,000 quasars, the data for that many quasars from data release 16. I recognize that the data may not be statistically representative because quasars are selected by telescopes, instruments available, location in the sky, brightness and size, and they're selected by computer algorithms. But it's fairly general information. There was no systematic effects that I was expecting to sort of impact the data. And let's not forget, there's 750,000 quasars out there with detailed data and high redshifts. So surely there's something to find. And let's start looking at the results. I did this for galaxies initially, and I found the counts were like this. So you can only count galaxies up to a redshift of about 1 because they are so faint, you can't see the more distant redshifts. And why we're seeing these peaks and troughs in the counts? I was flummoxed by that initially, and then I was told quite simply, this is due to the technologies used. So the Hubble Space Telescope is focused on measuring the parameters of more distant galaxies. The smaller telescopes based on Earth are measuring the nearby galaxies that are not so far away, and that smaller telescopes can measure. And then the larger telescopes based on Earth are measuring this middle peak that is counting and measuring the data for those galaxies that are in this mid-range. And as you can see, there's inconsistency between the use of the different telescopes, although it's amazing to me that Hubble has sort of measured and counted some information on so many galaxies at this region. And you can see here, tens of thousands of galaxies are in this range. And when I drew the same information for quasars, I found a different chart. Here you see the scale is different, it's smaller. And this is about 2.5 million galaxies. This is about 750,000 quasars. And you see them more evenly distributed across the redshift region. Many of you will have seen information in magazines and newspapers about quasars with redshifts of 5, 6, and 7, but they are very unique, really. You know, there's not many found at those distances. The vast majority are found with a redshift of less than 3. but still, much more than we can see with galaxies, because these things are so bright. There are some peaks and troughs a little bit here, and again, that reflects different instruments and telescopes that are used to measure and find quasars, but it is more evenly oriented than the information for galaxies. Now, having done all the introductions, let's look at counts of quasars at redshifts of 0.01 to 0.04. At 0.01, as you can see from the counts, there's hardly any quasars that close to Earth. As I said earlier, most of the quasars are very distant from us. And as we start looking at quasars at increasing redshifts, we can start to see some patterns emerge. And you see here, it's still low numbers, but we are starting to see that the few quasars that we have found are around a magnitude of about 15.7. And then when we look at the next increment, we count the quasars. And again, we see that there are groupings around, magnitude 16.2, 16.1. And so going from a distance of 0.02 to 0.03, it's fairly linear. We can see that we are seeing a change in the brightness of the objects being measured, which does indicate that there's a redshift distance relationship. And as we go out to 0.04, once again, it's a bit vague, but we can start seeing that the center of information, the counts are increasing, which is what we expected. The center is becoming less luminous. The counts are at a less luminous average. So this is intriguing information. So I went on. And let's see if we can do this. My computer's decided to take a little break. Bear with me. Here we go. So at 0.05, we can start to see the redshift at 0.05, a relationship that looks like it might be a normal distribution, which, going back to my introduction, this isn't like galaxies. This is quasars appear to be forming a normal distribution with a peak of counts at the center of that distribution. And then as we go through the redshifts, you'll see the normal distribution curves I've overlaid on the fairly noisy counts, but you also see the counts are now up to 40, and they're increasing as we go up the range. And I drew this data and found this relationship about the relationship between quasar counts and normal distributions. And I can't find anything similar in all the papers published around the world. And yet this data is available online from SDSS. Anybody else could have done the same analysis that I've done. Now, when you get up to about a redshift of 18, you see at 17, the normal distribution is there. And remember earlier I said there are telescope limitations. Well, in the next couple of, here we go, 19, we start seeing that the counts from about magnitude 18.5 onwards, getting fainter to the right, if you remember, are starting to drop off. And therefore the normal distribution curves I've drawn have been driven by the left-hand part of the normal distribution curve and given less weight to the right-hand side, because the counts, let me just point to them, in this region here are reduced because of the telescope ability to measure the data at those levels. But I hope, like me, there seems to be strong evidence that quasars do have, here's all the slides from 0.05 to 0.16, there is strong evidence to say there is a normal distribution effect for quasars at different distances from the Earth. And there it is for the higher redshifts. And it's still, when I say higher redshifts, that's only up to 0.25. Remembering that galaxies can be seen out to a redshift of 1. These quasars are relatively nearby to us. And the data I've used consists of about 10,000 quasars. It's not a couple hundred. it is 10,000, albeit split into the sizes of these increments here, so that the counts are of the order of 40 or more at the peak. So what else does this tell us? I have to go a little bit sideways again. Hubble's redshift distance relationship. From a theory point of view, I've drawn a couple of lines on this chart. And what that tells us is, if at a redshift of about 0.25, an object has a magnitude of about 15.9, then the same object would be seen at a redshift of 0.15 with a magnitude of about 17.9, and at about 0.25, its magnitude would be about 18.8. And this line is theory. And I've drawn another line here, which is theory. And when we start looking at galaxies and supernovae, we find these results superimposed on the theory lines. And you can see that the supernovae results for, this is again information I got off the internet, for supernovae with this redshift, this is the most common magnitude. And going along here, you can see it very nearly matches the lines, not so accurately at the end for the more distant objects. They appear fainter than expected, but that could be due to all sorts of factors. And down here, what I've drawn is the brightness of the brightest galaxies measured at various redshifts and reported in the Sloan Digital Sky Survey for galaxies. And again, you'll see that the measurements of the brightest galaxies very closely follow the theoretical line I drew earlier. So I found that useful to know that, and that the approach I'd used to sort of measure these statistics matched the theory. And then I put on this chart the data from the peaks that we measured from the Gaussian distribution, the normal distribution curves for quasars. And you see, yes, as the quasars get to higher redshifts, they get fainter. So there's a redshift distance relationship. But the relationship does not match the curves and the expectations that Hubble told us about and his calculations show. Although Hubble's curve does apply to supernovae at these same distances and the brightest galaxies. So what is happening? Why is this different for quasars? And to cut a long story short, I don't know. I wrote a paper about this and published it earlier this year. And I'll tell you a little bit more about my findings. But to be honest, I just don't know the answer. I've considered different things. And one of the things I looked at was, could I fit a Hubble theory to the actual values and measurements that we had? And here is a corrected best fit line that matches the data. And I made that best fit happen by setting a brightness for the brightest supernovae and adding a blue shift or a red shift to try and sort of find where was the best fit to this data. And I found that if I added a blue shift to the data points, then I was able to match a Hubble relationship to the quasar data that we got from the SDS survey. And that wasn't what I was expecting. I don't know that it's true that this is happening, but a blue shift of 0.06, which is a reduction of 0.06 in the data that we get from the SDS survey results, would indicate a fit of a Hubble relationship to the data. So that means quasars are 800 to 900 million light years further away from us than we previously thought. Bearing in mind our galaxy is only 100,000 light years across, and there's loads of galaxies in the near vicinity, that is really saying that quasars are a very, very long way away from us. So coming towards the end of the presentation, the SDS data tells us that 10,000 quasars that were used to create the results I've just shown you are consistently showing a normal distribution at each redshift increment. I haven't seen that reported before. The counts increase and the peak of the counts moves as redshift increases. So that indicates there's a redshift distance relationship, but is not the expected Hubble redshift distance relationship. I've not seen that reported anywhere before. And as I'll show you a little bit more data in a moment, the peak quasar luminosity is fainter than that of the brightest galaxies in the redshift range 0 to 0.25. That is interesting because as we get to higher redshifts, we see quasars that are brighter than the brightest galaxies. So why are we seeing quasars that are not brighter than the brightest galaxies in the near distance, in the distance only to 0.25 redshift? So this leads to new questions. Why is it not the same? Why is Hubble's law not being applied at nearby quasars? Are quasars further away than we think? Maybe, maybe not. And can we believe these results because it's just David Youll in Basingstoke analyzing the data? Can he have made a mistake? And yet he's analyzed the galaxies and the supernovae and come up with similar results. And as I'll show you in a moment, the low redshift quasars are not consistent with high redshift data. So let's look at the data from 740,000 other quasars. But to do that, I've got to show you two more diagrams, and then we'll be finished. This diagram asks you to bend your mind a little bit and look at the data in a slightly different way. What I've got up the left-hand side is brightness, and along the bottom is the redshifts. And what I've done is to show as a contour map the level of counts at different points. So the blue region is low counts, the orange region, the counts are a little bit higher. So it's just like a contour map of a hillside. And the dotted red line I've added here shows you, pardon me, the line where the peak count occurs. And that's the sort of relationship we see for the low redshift quasars. Now the next slide shows you the same data down here, and then there's information across the page here up to redshift 3.5 of the counts for all the other data available from the Sloan Digital Sky Survey. And you'll see here the blue line represents the data I mentioned earlier about the brightest galaxies in the universe. And as you see, as we get out to a redshift of 1, we're getting up to a level of a magnitude of 19, which is so faint that we can't really count galaxies after this point, and the line would get even further up. And this is the line for supernovae. And we see in this region here, up to a redshift of 0.25, most of the quasars are found. And yet when we come to higher redshift, we're seeing quasars are being found with brightness at magnitude 17, which is much brighter than the brightest galaxies we would expect to see at that level. What's going on? I just cannot explain that at all, but there's definitely a tail in the counts that you can see here, and there's definitely a relationship here that I showed you earlier. So quasars are full of conundrums. So there is a redshift distance relationship. And I believe we should not consider the redshift of quasars to be always wholly related to distance using Hubble's law. And more data is required to actually get to the bottom of what that data is really telling us. All I've done is identify that there are inconsistencies in the data, and we need to investigate further. So we're almost finished. This is not a real picture. This is a diagram of what a quasar might look like if only we could get a bit closer to it. And it shows at the center, potentially a massive black hole with a spinning disk of debris around it and bright plumes of light and potentially matter being ejected in different directions from that object. Might a quasar look like this? I don't know. I did send my paper to the SDSS team for review, and I was pleased to get a response from a professor of astronomy and astrophysics in the USA, who's been a long-term member of the SES team and a former chairman of its Quasar working group. He's now close to retirement, if not retired. He's about the same age as me. And he wrote many papers back in the late 90s and 2000s about quasars. And he was once ranked #2, so he's well read. And I sent him my paper for review, and he said, "The results in your study are so astonishing that, if true, would invalidate much of the 50 years of research in this area. And given this situation, you must be quite certain that you are interpreting the data correctly. So I give you that warning. I think my interpretation is very straightforward and accurate. And I think quasar astronomers have a lot to sort of discuss and respond to the paper I've published." So to finish off with some further reading, my paper was published in the Journal of High Energy Physics, Gravitation and Cosmology. I've published my paper about quasars and my paper about galaxies on ResearchGate. And if you want to find out more about the SDSS survey and its data, then that's available there. And if you're interested in doing your own research with the data available from SDSS, the next release is coming in December 2021. So get your laptops upgraded and ready to process all the data that will be coming out at that time. I should acknowledge that SDSS was the source of my data, and they require you to publish this acknowledgement on every paper that was published. And then finally, any questions? So I'll end my presentation there and hand back to Bob for management of the next few minutes.
Excellent. Thank you very much, David. That's sort of fascinating and yes, interesting results there. We only had one question come in during the talk. I didn't want to interrupt you. And it's from Stefan Lloyd saying, what characterizes a quasar in SDSS? Like, how do you know one when you see one?
Well, the basic elements are its size and shape, the visible size and shape. It's compact, and there's no galactic sort of spread. It is just a point source of light, and it is that spectrum. It is, they measure the spectrum and they see, the balance of X-rays and ultraviolet rays and normal light. They take all these factors into account. And the characteristics, I couldn't define them specifically to you, but that is the set of characteristics that are used.
Excellent. Well, with that, I'll open up questions to the rest of the society. Open up questions to the rest of the society.
Would it be possible to send those?
Would it be possible to send those?
The links to your research papers via the WhatsApp or the email?
Certainly, I can do that. That's very easy.